Hi, in this video I'm going to introduce you to some unusual compounds that don't look like benzene but are still aromatic. In other words, they have the properties of being more stable than you would otherwise expect and doing reactions that are not what you would expect for compounds with double bonds. But I'm going to start out with some facts, some interesting observations that have been made over the years, and then we will try to see if we can come up with some generalizations about compounds that have these properties. And then we'll look a little bit at the theory about why these compounds are in fact aromatic, even though they don't look like it based on their structure. So let's start with some compounds that have more than one benzene ring hooked together. For example, here's a 10 carbon compound with 2 rings and 1, 2, 3, 4, 5 double bonds. This compound is called naphthalene. And that's a name you should memorize. And by the way, we will talk about naming of aromatic compounds because it's a little complicated and there are a bunch of things to memorize in another video. But for now, just learn that that's called naphthalene. Notice that it really is just 2 benzene rings hooked together, so it shouldn't be too surprising that that's aromatic. It has the same properties of extra stability and doing different reactions than we would expect, pretty much being unreactive to most things. Here's another one called anthracene. By the way, I misspelled naphthalene. It should be E-N-E. Notice that these names and any other ones like benzene have the E-N-E ending, which makes them seem like they're alkenes, but they're not. They don't act like alkenes in any way. Neither do these. This is really just 3 benzene rings hooked together. Notice sharing 2 carbons in each case. These are what are referred to as fused ring systems, meaning they share 2 carbons between the rings. And then there's another one that's similar to anthracene. In fact, it's an isomer. If we just hook the 3 benzene rings together, but kind of around the corner, that's called phenanthrene. And kind of an odd name, sort of systematic, sort of not. I'll let you think about why it might be called phenanthrene and why it shouldn't be called phenanthrene, but we'll leave it at that for the moment. These 2 are both the same formula, so they are in fact isomers of each other, both aromatic. By the way, you can draw more resonance structures for naphthalene. In fact, you can draw 2 more resonance structures than this one. You should go ahead and see if you can draw those resonance structures. And you can draw several resonance structures for anthracene and several resonance structures for phenanthrene, and I'll let you do that as well. And basically, the rule says that the more resonance structures you can draw, the more stable it is, and that's one way of explaining the aromaticity of these compounds. But it's going to turn out that not everything like this is aromatic. Sometimes they have exactly the opposite properties. So these are aromatic compounds. Notice, if you will, the total number of pi electrons, and this is conjugated all the way around because it has p orbitals at each of these carbons. So we can put our finger there and go all the way around with p orbitals. So it is, quote, conjugated all the way around, unquote. And it has how many total pi electrons? 2, 4, 6, 8, 10. So let's make note of that, 10 pi electrons. What about benzene? As we saw in the last video, 6 pi electrons. Those numbers are going to be important here in a little bit. How many pi electrons? Oh, by the way, conjugated all the way around. P orbitals, starting here, you can go all the way around. Every single carbon atom in the ring has a p orbital, so it's conjugated all the way around like a picket fence. That's important. And it has how many total electrons? 2, 4, 6, 8, 10, 12, 14 electrons. And these are pi electrons I'm counting. Of course, it has a lot more than that in terms of sigma electrons. Same thing here, conjugated all the way around. You can put your finger on right there. That has a p orbital, as do all of these carbons, all the way around, all the way back to there. P orbitals all the way around, therefore conjugated all the way around, and also having 14 pi electrons. Okay, so just keep those numbers in the back of your head. You can go ahead and draw lots more isomers that have more than 4 benzene rings fused together in all sorts of different arrangements, 4, 5, 6, and so on. And what you will find is that they will all have 6, 10, 14, 18, 22, 26, and so on. And you begin to see a pattern there. Okay? Keep those numbers in mind. Okay, so these are really not that unusual. They are what are called polycyclic aromatic. Hydrocarbons. And of course they're hydrocarbons because they only have carbon and hydrogen. Polycyclic because they have more than one ring, obviously except benzene. And aromatic because they're all aromatic. For short, that's PAH. And you often hear about how PAHs tend to be carcinogenic, and it's true they are. Not so much naphthalene, but anything higher than that, those tend to be carcinogenic, so we try to avoid it. Unfortunately, when you grill meat on charcoal, for example, you get lots of PAHs. Also, if you smoke cigarettes, you get lots of PAHs in your lungs. Obviously, that's a bad thing. Let's move on to some other classes of compounds that may not even appear to be like benzene at all, but do in fact have properties similar to benzene. These are going to be called non-benzenoid aromatics. I'll write that word on the board. Oh. Non-benzenoid aromatics. That means, you know what oid means, it means like, so these are not like benzene, non-benzenoid aromatics. Let me give you an example. If you make a compound that looks kind of like naphthalene, except it doesn't have a bond in the middle, so it's just a plain old 10-membered ring. It's a big ring, obviously, but it can be made, and you put double bonds in such a way that it is double, single, double, single, double, single, double, single, double, single, and so on, all the way around the ring. Again, a p orbital at each of those 10 carbon atoms, and conjugated all the way around. Okay. This is a compound called 10-annuline. Annual is sort of an old-fashioned term for ring, so this is a 10-membered ring, 10-annuline. It also would have an IUPAC name, which would be something like Cyclo Pentadiene, meaning 10 rings in a cycle and 5 double bonds, so Cyclo Pentadiene. But most people would just call it 10-annuline. Okay. Turns out that it's more stable than you would otherwise expect. It doesn't really react like an alkene. Okay. And similarly, if you had 14 members in a ring, one, two, three, 4, 5, 6, 7. 14-membered ring with 7 double bonds, again conjugated all the way around. And by the way, you can draw rings of all sorts of different sizes and different shapes. This would be called 14-annuline, meaning 14 members in a ring with enough double bonds to be conjugated all the way around, double, single, double. That's what the annuline means. By the way, using that same system, you could call benzene, what would you call that? You'd call it 6-annuline. Nobody calls it that, they call it benzene, but technically it follows in that same pattern. And notice the numbers of electrons here, 10 electrons, 14 electrons, you could make one with 18 electrons and so on, same numbers that we saw a few minutes ago. But what about other ones that don't have those numbers? For example, how about an 8-membered ring? That's not aromatic. It turns out it's just like an alkene. It reacts like alkenes. It isn't particularly stable. You could call it 8-annuline, but they don't because it's not aromatic. They call it cyclo tetraene. And it's a perfectly fine compound. It's just not aromatic. It doesn't have the extra stability and it reacts like an alkene, whereas these other ones don't. What about a 4-membered ring with 2 double bonds? Now that's very interesting. This is called cyclo Pentadiene. Again, using the IUPAC system, 4 members in a ring, so cyclobuta, and then 2 double bonds, so diene. Turns out cyclobutadiene, unlike these, which are aromatic and very stable, and unlike this one, which is not aromatic, but just a regular old compound, this one is fiercely unstable. It's really never even been made, it's so unstable. It has been made under certain conditions and detected under very high energy conditions, but it turns out to be so much less stable than we would expect that it's what's called anti-aromatic. And notice that it has 6 pi electrons. Oh, I'm sorry, 4 pi electrons, and this one has 8 pi electrons. So 4 and 8 are bad numbers. 6, 10, 14, 18, and so on are good numbers. By the way, we're going to learn these numbers, might as well learn the secret of it right now. There are certain numbers that are called Huckle numbers, which are the number of electrons in the conjugated pi system, which is conjugated all the way around. Huckle numbers are good numbers, which make things be aromatic. The Huckle numbers are 2, 6, as in benzene, 6 pi electrons, 10, as in naphthalene or in 10-annuline, which is a good compound, 14, as in anthracene or in 14-annuline, which are good compounds, 18, 20, 22, and so on. Okay, so you see a pattern there, 2, 6, 10, 14, 18, 20. Those are called Huckle numbers. Huckle was a German chemist who first discovered this phenomenon. And then there are certain numbers that are called anti-Huckle, and they give rise to what are called anti-aromatic compounds. And those are 4, as in Cyclo Pentadiene, 8, as in Cyclo Pentadiene, 12, which is, we haven't seen any examples of, but which is also an anti-aromatic number, 16, 20, and so on. So you see the pattern here. 2 is good, 4 is bad, 6 is good, 8 is bad, 10 is good, 12 is bad, 14 is good, and so on. Now there's a little formula, as you might guess. These numbers all follow the pattern of 4n plus 2, where n is any number starting with 0, 1, 2, and on up from there. So if n is 0, then this number is 2, and there it is. If n is 1, then this number is 6, and there it is. If n is 2, this number is 8 plus 2, 10, and there it is. Whereas these all follow the pattern of 4n, where obviously each one of those anti-Huckle numbers or bad numbers is divisible by 4, so we can use the formula 4n for those. Weird. When Huckle discovered this, he had no idea why it worked this way. It just does. Let me give you some other examples of interesting non-benzenoid compounds. Besides the annulenes, which are really just big rings with conjugated double bonds all the way around, they may be good or they may be bad, but they have to be conjugated all the way around, and to be aromatic, they have to have a Huckle number. But here's an interesting compound. What if we have a 5-membered ring and a 7-membered ring fused together? So neither one of them is a 6-membered ring, but a 5 and a 7. Notice that we could start with a p orbital here and have p orbitals all the way around. So it is in fact, quote, conjugated all the way around. And it has how many total pi electrons? 2, 4, 6, 8, 10. That's a Huckle number. Turns out this is particularly stable. So it is in fact what we call aromatic. It's a very interesting compound. Unlike most organic compounds, which are white or colorless, this happens to have a really beautiful bluish green color. In fact, I don't know if you're familiar with the color called azure, but azure is a bluish green color. This compound is called azulene, and it's a pretty stable compound, as you might guess from the fact that it is in fact aromatic. Okay. What about a compound like this? This has been made, and it's a reddish, unstable liquid, very beautiful but dangerous because it's so unstable. This is a compound that's known as pentylene, I guess because of the fact that it has 2 5-membered rings, it's called pentylene. By the way, these are not IUPAC names, as you might guess. It turns out pentylene is conjugated all the way around, right? P on this carbon and p orbitals all the way around. So it is conjugated all the way around, but it has how many total electrons? 2, 4, 6, 8. That's an anti-Huckle number. It turns out this is anti-aromatic. It's very unstable. And as I said, it has been made, but it reacts with just about anything that it comes in contact with, including water vapor and including oxygen from the air and all sorts of stuff. So it's anti-aromatic. What would you guess about a compound that had two 7-numbered rings? Conjugate all the way around. Double, single, double, single, double, single, double, single, double, single, double. What do you think? Well, it's conjugated all the way around, so it has a chance of being aromatic or possibly anti-aromatic. How many pi electrons? 2, 4, 6, 8, 10, 12. That's an anti-Huckle number. Turns out this compound is very unstable, almost as unstable as pentylene is. So it's anti-aromatic. I don't remember what the name of that is, so we won't worry about it right now. So those are some interesting compounds in and of themselves. Then it turns out there are a whole class, and by the way, you could draw other ones in which you have various sizes of rings fused together. You could have a 5 fused to a 6, fused to another 5, or a 5 fused to a 7, fused to a 6, and all sorts of things like that. And as long as you can draw double bonds all the way around, it will either be anti-aromatic or aromatic, and it depends on the number of pi electrons in the delocalized system. Let's learn about some other compounds. These are even stranger to be aromatic, but there's a compound called furan, and that's a name you should learn. Furan is a 5-membered ring, but it has an oxygen as one of the members. So this is one example of many, many, many compounds, and we will learn about more of them as we go along, called heterocyclic. I think we've used that term before. Heterocyclic means ring system, but at least one of the atoms in the ring is not carbon. So in this case, the one is not carbon, is in fact an oxygen. I'm going to go ahead and draw lone pairs on there and double bonds, because that's furan. It has 2 double bonds and an oxygen in a 5-membered ring. It turns out furan is very stable, or at least way more stable than we would expect for an ether. Because notice this has carbon, single bonded oxygen, single bonded to carbon, so technically it's an ether, but it's way more stable than most ethers are. And it also doesn't react with compounds or with reagents that you might expect double bonds to react with. So it also has the same sort of properties that benzene has. So how many pi electrons in the system? First of all, is it conjugated all the way around? Does it have a p orbital at that oxygen right there? Or saying it another way, is this an sp2 hybridized atom? Your first guess, I'm thinking, will be no, it's not. It should be an sp3 hybridized atom because it has 1, 2, 3, 4 groups of electrons around it, and you've learned that 4 means tetrahedral, which means sp3. In fact, it's sp2. Now, I don't know if that bothers you, if you're throwing up your hands and saying, oh no, I thought I knew how to figure out sp, sp2, and sp3, but now he's telling me that this is sp2. Well, here's the thing. If it can become conjugated by switching to sp2, then it will do that. In other words, if it can have a p orbital, which will then overlap with a p orbital on a carbon atom next door, then it will do that because that's a good thing. Overlapping p orbitals is good, and so it will do what's called rehybridize. It will go from being what you would originally thought it was, hybridize, to a different hybridization so that it can in fact be overlapping, and that's what it does there. It becomes sp2. So let's take a look at the balloon picture for this. I'm not going to worry about the sigma bonds, but let's look at the ring system and realize that there are p orbitals at those 2 carbons representing that double bond, p orbitals at those 2 carbons representing that double bond, and then this oxygen, which normally would be sp3, switches to being sp2, so it has a p orbital sticking up and down, and it has a p orbital pointing out. In the plane of the ring, like here's the plane of the 5-membered ring, the sp2 orbital is sticking out like a sore thumb, sticking out like that. Okay. Let's put electrons in, 1 in each of those for the 4 double bonds, 2 in this p orbital, representing that pair of electrons, and 2 in the sp2 orbital, representing that pair of electrons. So in other words, these 2 pairs are not the same as each other. Here's a little trick. Notice that that pair is drawn inside the ring, geometrically inside the ring, and therefore you can guess that it's probably part of the aromatic system. So notice, let's count the pi electrons. 2, 4, plus those 2 right there. That's 6. That's a Huckle number. And therefore this is in fact aromatic. Conjugated all the way around with a total of 6 pi electrons. 1, 2, 3, 4, 5, 6. Therefore aromatic. And it turns out furan, as I said, is more stable than you would otherwise expect. So it is in fact aromatic. Okay. We will, in a future video, look at the molecular orbital scheme for furan and other 5-numbered rings that happen to have 6 electrons in them. And it all will fit together, it all makes perfect sense. But we won't do the molecular orbital scheme just yet. I want to show you a few other compounds and have you decide whether they are aromatic or not. Okay, so that's furan. Let's take another compound, also with a 5-membered ring, but with a nitrogen in it. And let's attach something else on there, like a hydrogen or a methyl group. Let's just call it R. That could be just about anything you want it to. 2 double bonds, and remember nitrogen will always have 3 single bonds and 1 lone pair if it's a neutral nitrogen, no charge on it. So, and this compound without the R group on there is called pyrrole, P-Y-R-R-O-L-E. I'm sorry, I think it just has 1 R. Pyrrole. Okay. Is that aromatic or not? And the answer is yes. It's conjugated all the way around. That nitrogen, again, you would expect to be sp3, but because if it becomes sp2, it will have a p orbital sticking up and down. It can become conjugated with the other p orbitals in the ring and become aromatic, and being aromatic is a good thing. So in fact, it has 6 pi electrons, and that's a Huckle number. Okay. So pyrrole is also aromatic. Here's another interesting compound. I'll leave that one up there for the moment, and I'll leave the number 6 there as well. What about a 6-membered ring with a nitrogen and 3 double bonds? Now notice that that compound looks a lot like benzene. It's a 6-membered ring with 3 double bonds. It's just that one of the 6 carbons is a nitrogen. And if it's going to be a neutral nitrogen, it has to have a lone pair on it. In other words, nitrogens always have, what, 3 bonds and 1 lone pair to be neutral. So is this compound aromatic or not? Question is, do we count that lone pair as part of the aromatic system? And the answer is no. Here, sort of a tricky way of knowing that, or sort of a rule of thumb, is because it's drawn outside the ring, it's not part of the aromatic system, whereas this one's drawn inside the ring, so it is part of the aromatic system, but you can't always count on that being that way. People won't necessarily draw it that way to make it easier for you. But what we can do is look at the balloon picture for this and see what kind of orbital that pair of electrons would have to be in. So here's our 6-membered ring, and again I've drawn it kind of flat and parallel to the floor. Each of these atoms has a p orbital sticking up and down, including the nitrogen. And I say it has a p orbital on it because that is in fact sp2 hybridized, and there's no question of rehybridization or anything like that. It just is sp2, and that's what you would expect. And then that lone pair is in an sp2 orbital sticking out in the plane of the ring, like that. Okay? Much like the second pair of oxygen was in the furan that I had on the board a minute ago, and you might want to review that part. But then each of these p orbitals has 1 electron in it for a total of 6, 2, 4, 6. And the pi system, the delocalized, conjugated all the way around part, has in fact 6 electrons, and this pair is not included in that delocalization, so it's not counted in the 6 electrons, and so this also has 6 electrons, and therefore it is also aromatic. That one may be a little bit less surprising because it really does look a lot like benzene, doesn't it? This one, also aromatic, not necessarily what you would expect, but because it has 6 pi electrons, it is in fact aromatic. Okay. Now I'll give you one that's a little bit trickier. Another heterocyclic compound, which, by the way, pyrrole, oh, I didn't name this one for you. This is pyridine. We've run across it before, just as a base that can pick up an H+ in some reactions, and it's because of that pair right there that makes it basic. Okay, so that's pyridine, also aromatic. And you can imagine all sorts of 5- and 6-membered rings with all sorts of heteroatoms in them. Like, for example, if we had a nitrogen and an oxygen in a 5-membered ring, and the double bonds were located there, and we had a lone pair on that nitrogen and 2 lone pairs on that oxygen, would that be aromatic or not? And the answer is yes. which are the electrons that we count. We count those two, and those two, all in the aromatic ring. This one is in an sp2 hybridized orbital sticking out parallel to the ring, and this one's also in an sp2 hybridized orbital sticking out parallel to the ring. Those two are in a p orbital along with the p orbitals on each of these other atoms. So 5 atoms, 6 electrons in that conjugated all the way around system, and therefore aromatic. There are lots of other more complicated ring systems, and you can even have fused ring systems in which maybe you have 2 6-membered rings fused together, or a 6 and a 5-membered ring fused together with different heteroatoms in them. But basically the rule is count a pair of electrons on a heteroatom if you need it to be aromatic. That's essentially what the rule is going to say. Okay, now let me give you some other interesting facts. First of all, let's take a look at this compound. This is a 5-membered ring with 2 double bonds, but that's a carbon, and that carbon, being neutral, has to have 2 hydrogens on it. So is that system aromatic, or perhaps anti-aromatic, or perhaps not either, which we would just refer to as non-aromatic? Well, how many pi electrons does it have? 2 in that double bond, 2 in that double bond. No lone pairs, no heteroatoms, nothing else to worry about, so just 4 electrons. That's an anti-Huckle number. So with this compound, which by the way is called Cyclo Pentadiene, that should sound familiar because we used it in the Diels-Alder reaction last week. But Cyclo Pentadiene, this is the compound. It turns out it's non-aromatic. You might guess it was anti-aromatic because of the 4 electrons, but notice that because that carbon has to be sp3, doesn't have any lone pairs, so it can't rehybridize, so it has to be sp3. It's not conjugated all the way around. It's just a regular old diene. It's conjugated, double, single, double, but not conjugated all the way around. So this is non-aromatic. Okay. But here's the interesting point. If you take Cyclo Pentadiene and you react it with a base, and I think hydroxide is probably a strong enough base to do this, but most people would use like sodium amide or some other really strong base, maybe sodium hydride. You can actually pull off one of those hydrogens and form the conjugate base at that position, in which case then we'd only have 1 hydrogen and a negative charge on there. So this is an example of a negative carbon molecule, and we refer to those as carbanions. So this is a carbanion. But it turns out to be a pretty easy carbanion to make. Most carbanions, as you may remember, are not stable. They are really hard to make. You have to use really, really strong bases to make carbanions. But in this case, you don't have to use a particularly strong base to do it. So why? Why is that such a good carbanion? It's aromatic, right? 2, 4, 6 pi electrons. This carbon is going to rehybridize and it's going to become sp2. And it's going to do that on purpose so that it will have a p orbital sticking up and down so that it can overlap with the rest of the p orbitals in the ring system. And then it becomes p orbitals conjugate all the way around, and 2, 4, 6 Huckle number of electrons. That's good. So this anion is in fact aromatic. Okay. Doesn't look anything like benzene, but if you kind of look at it, you see, well, it sort of does. It's got these 6 electrons in a conjugated ring, and so that's aromatic. Okay. Let's leave that on the board and let's do a different situation. What if we started with a 7-membered ring with 3 double bonds and 2 hydrogens at that position? Again, that compound itself, which we would refer to as cycloheptatriene, 7 carbons, 3 double bonds, so cycloheptatriene, is neither aromatic nor anti-aromatic because that carbon is sp3. It's not conjugated all the way around, so it's just non-aromatic. But if we react this with a base, can we pull off one of those H pluses to make it a carbanion, just like we did down here? We can certainly draw the picture. That would have now 1 hydrogen and 3 double bonds all the way around. Conjugated, sp2 and p orbitals all the way around. Is that possible? And the answer is no. This does not happen. Oh, that would have a negative charge. The answer is it does not happen. Why not? because that would not be aromatic. In fact, if it formed and if it was flat, so it could be conjugated all the way around, that would have 8 pi electrons, and that's an anti-Huckle number. That's bad. And so that doesn't happen. So starting with a 5-membered ring and 2 double bonds, it does. A 7-membered ring and 3 double bonds does not. Even a 3-membered ring with 1 double bond, which in itself seems really unstable and unlikely to even exist, and yet it does. It's pretty unstable. It's a very high energy molecule, but it does exist, and you can in fact treat it with hydroxide or some other base. It's not limited to hydroxide. And the question is, can we pull off an H+ from there to make a carbanion that would be aromatic and therefore stabilized? Negative charge on there, hydrogen, and of course hydrogen on each of these carbons, just like there's hydrogen on each of these carbons, and in the 5-membered ring also 1 hydrogen on each of those carbons. And a double bond. What do you think? Aromatic or not? And the answer is no. It is conjugated, but it has 4, an anti-Huckle number, so in fact that doesn't happen. Okay. So what we've learned from this is that you can sometimes make carbanions that are aromatic as long as they have a Huckle number and are conjugated all the way around. Let's look at another set of molecules and a couple of reactions. What if we start with, again, a 5-membered ring with 2 double bonds, but a chlorine on there. Instead of 2 hydrogens, we have a hydrogen and a chlorine. Not aromatic or anti-aromatic because, again, sp3 hybridized carbon, it's not conjugated all the way around. But what if we react this with some polar solvent, like let's just say water? If we put that into water, will this do an SN1 reaction? The chlorine come off to form a carbon cation, and then water attack to replace the chlorine. This would be an old reaction that we learned months ago now, called an SN1, nucleophilic substitution. That might be the product you would expect. Does that in fact happen? The answer is no. It's very slow if it happens at all. No, it doesn't happen. Why not? Well, if this were indeed SN1, that would require a carbocation. The halide would leave first, forming a positive charge at that carbon. So the intermediate in the mechanism would look like that. Just that hydrogen remaining, and of course hydrogen at each of those other positions. sp2 hybridized, p orbitals all the way around, conjugated all the way around. How many total pi electrons? 2, 4. Any pi electrons there on that one? Nope, it's just a positive charge, so no extra electrons. Empty p orbital there. 4 pi electrons, anti-Huckle number, doesn't happen. But what about a 7-membered ring with a chlorine and a hydrogen and 3 double bonds, and of course hydrogens at each of those positions? If we react that with water, does it form the alcohol that we might expect from a normal alkyl halide? And the answer is yes. Happens like a shot, very fast, easy, efficient reaction. This kind of alkyl halide forms that kind of alcohol very quickly. Why? Because the intermediate in an SN1 type substitution would be that carbocation. Notice conjugated all the way around because that would have a p orbital at that particular position. How many pi electrons? 2, 4, 6. None at that carbon, so just 6 pi electrons. 6 is a Huckle number. This carbocation is aromatic, forms very readily, and therefore this reaction happens very readily because the carbocation is a good one. What about a 3-membered ring with a double bond and a hydrogen on each corner and a positive charge? What do you think about that carbocation? Again, looks pretty bad because the angle strain would be terrible in that 3-membered ring, especially with a double bond in it. But the fact that it has 2 pi electrons in a 3p orbital system conjugated all the way around means that this is in fact aromatic. And that's really not that unusual of an ion. Now it is pretty bad because it's strained, but it has way more stability than you would otherwise expect based on the fact that it has a Huckle number of 2, and it is conjugated all the way around, therefore it is in fact aromatic. Okay, one thing I didn't talk about in this video, basically I'm done, but I want you to remember that anytime you have an aromatic, or for that matter an anti-aromatic molecule, you can draw more than one resonance structure, and particularly with these odd-numbered rings with positive or negative charges, you can draw usually many resonance structures for them. So just to practice this particular one, and I won't draw it out for you, but you'll be able to draw 6 more resonance structures. And you should go ahead and do that just for practice. Draw the 6 resonance structures for that. And similarly for the Cyclo Pentadiene carbocation, positive charge. Again, 2 double bonds, hydrogens all around. You'll be able to draw 4 more resonance structures for that. Even though it's not aromatic, it's in fact anti-aromatic, you can draw more resonance structures for it. So we have a problem here. Remember the rule of thumb of resonance structure says the more resonance structures you can draw, the better. Well, you can draw a ton of resonance structures for this one, and yet it's still really unstable, doesn't form, it's a bad molecule. So that kind of goes against the rule that says the more resonance structures you can draw, the better. So what we're going to have to do in order to understand why are these Huckle numbers the way they are, and why, even though we can draw a bunch of resonance structures for one of those bad anti-Huckle numbers, it's not a good thing, it's bad. We'll have to use molecular orbitals to explain that, and we will do that in the next video. Thank you for your attention.